Welcome back. It's Intro to Physical Anthropology. I'm your instructor, David Leitner. Today, we are talking about what is a species and are they made? Pretty big question, pretty sort of fundamental thing in evolution. Let's not waste any time and go ahead and get started. All right. The most popularly accepted definition of a species comes from Ernst Mayr, 1942. Ernst Mayr is the father of the neo-Darwinian synthesis, which sort of brought our growing knowledge of genetics at the time in line with what we knew about evolution at that point. And it was kind of a revolutionary thing. Finally, people were looking at genetics as an evolutionary thing, and it really revolutionized biology. Anyway, so it's quite natural he would come up with a term, or come up with the definition for the term species. So for him, it is, and I'm going to highlight some pieces here as I go on, an interbreeding group of animals or plants that are reproductively isolated through anatomy, ecology, behavior, or geographic distribution from all other such groups. Now, the important points there are interbreeding and reproductively isolated, particularly the second one. So, but before we get into that, let me sort of point out that this is not the only definition for species. There are currently at least 25 or more proposed definitions that have been published in the literature. Mayer's is sometimes referred to as the biological species concept. There is an evolutionary species concept, because when you're studying evolution, particularly things like paleontology, you can't always identify a lot of things that would be traits if you're identifying living organisms. So, evolutionary biologists oftentimes are looking for very distinct differences, much more distinct than otherwise, because of the problems with knowing whether fossils are a good representation of an actual population or whether it's just a sort of a fluke that you have this thing. So in the evolutionary species concept, we can't observe them interbreeding, so we don't know. So we have to look for really significant evolutionary identities for them. The ecological species concept focuses on how every organism occupies its ecological niche. And in that sense, sometimes you could have what might be the same species in the biological species concept be looked at as almost two different species if they occupy two different niches in the range. So if they perform a different function in the ecology, an ecological species concept might make that two different species. Finally, the recognition species concept, and these are just a few. These are just the few most common. The recognition species concept that says that it's not enough for them to potentially interbreed. They have to recognize each other as potential mates. If they can't recognize each other as mates, it's not going to happen. It's not a species. So, but all of it really hinges on this idea of interbreeding and hybridization. Okay, so if reproduction is so important, let's talk about what reproductively isolated means in that definition. Okay, well, in biology, we look at the things that separate species as reproductive isolating mechanisms, or RIMs for short. They are any factor that prevents a male and female of two different species from hybridizing. So that feature of being able to hybridize, that is to interbreed, is important. And of course, it can't just be interbreeding one time. It has to be that the offspring themselves can produce viable offspring. Otherwise, it's kind of a dead end, right? So mules are the result of interbreeding between a horse and a donkey, but they are almost always sterile. So it's not really a separate species. Okay. Reproductive isolating mechanisms come in two flavors. There are those that are pre-mating and those that are post-mating. Okay. Pre-mating rims are things like habitat isolation. You live on an island, the other population lives on the mainland. Doesn't matter how closely related you are, you're never going to meet. Temporal isolation. Your group comes out at night, my group comes out during the day. Your group mates in the spring, my mates in the early summer. Things don't match up. Behavioral isolation. A lot of species recognize each other through song or sound or smells or what have you. If that isn't working, then there's going to be isolation. There's a great example of this on the island of Hawaii, where there's two species of cricket which genetically virtually identical. Like you would not be able to look at their genes and be like, they're two different species. But behaviorally, they have two very different songs. One is a higher register, one's a lower register, and it's because their original songs were kind of drowned out by some of the noise of civilization around. So these genetically almost identical species are separate species because the females will not respond to the male's sound if it's the sound of the other species. So they could potentially interbreed. There's nothing stopping them except the song. So finally, you've got mechanical incompatibility, which, if I'm being a bit indelicate here, is that the parts don't match. In fact, actually, if you look at, I wouldn't just Google this, but if you look into some of the research on the range of the evolution of the penis and the vagina, or cloaca even, various genitals, they look so different in different species, and they do very different things. Insects especially have crazy sort of alien art sculpture looking appendages. So like I say, don't just Google it willy-nilly. You may not like what you get, but maybe put safe search on. Post-mating rims. Okay, so you do actually manage to mate. Perfect, but that's not the end of the story. Sperm and egg have to be compatible. Sometimes they're completely incompatible, so fertilization never happens. Zygote inviability. Fertilization happens, but it never really gets started. Embryonic or fetal inviability. Again, fertilization occurs. Viable zygote gets out of the zygote stage, goes into embryo or even fetus stage, and then fails. Finally, offspring viability is just what it says. They may come to full term, but they cannot live to reproduce. And finally, offspring sterility. They live perfectly long lives, but they will not produce offspring. So there are a lot of things that can create reproductive isolation and thus spur speciation. Now, there are two different ways that species can be formed. The first is anagenesis. Anagenesis is like the long line down here. You'll see that over time, the species will sort of change. The time is on the y-axis and morphology on the... Actually, do I have this? Anyways, time is vertical, morphology horizontal. The shape changes over time, but no branching occurs. It's all within the same species. So if you went back in time and took an individual from back here at the beginning and tried to mate them with an individual up here at the end, they may not recognize each other as mates. It could be that the changes were that drastic. The other kind is cladogenesis. This is more classically, I think, what people think of when they think of evolution and speciation, that one group splits into two. Okay, and that is called cladogenesis because, as we learned in one of the other videos, clado means branching, okay? And genesis means formation, so it's a branching formation of species. Okay, that's what speciation looks like in terms of an evolutionary timeline. What does it look like in terms of the population genetics and the distribution of alleles? Well, you can have allopatric speciation, which is the result of geographic isolation. One population becomes two, they cannot have any contact with one another, no gene flow. Mutations accumulate in both species over time, and then when the isolation ends, they now no longer recognize each other as either some reproductive isolating mechanism comes into play. Parapatric speciation. There is a continuous distribution of genes throughout the species, but there are different selective pressures in some parts of the range. So there's a new niche entered into by this population, but the niche is ecologically very different from the traditional niche. So selective pressures are necessarily different. Over time, that portion of the population, the new genes become much more prevalent, and if they remain to the extent that it more or less isolates the individuals at the far end of the range from the other individuals in the rest of the range. So you effectively get a reproductive isolating mechanism with continuous range. Then if gene flow does occur, it's not going to occur very easily. So you're going to have this mixing, this zone of hybrids here as they come back together. Finally, sympatric speciation isn't a big thing in animals, but in plants it can be, especially plants that drop their seeds relatively close to the mother plant. In this case, you get an adaptation that occurs in one plant in part of a range that might be slightly different. Say you've got a boggy area in the middle of this open field here, and this adaptation allows the plant to thrive a little better in boggy areas. Well, it's going to pass those genes on, and those offspring will be dropped nearby, and then they will have offspring dropped nearby, and eventually you start getting this zone where these new genes are most prevalent, and over time it can sort of separate them enough that they become isolated, so you have speciation occur. So those are all three different ways that speciation can occur. Now, one of the big questions, even since Darwin's time, has been, what is the tempo of speciation? How often does it happen? And when we say how often, we need to be careful. We're not talking necessarily about time. The rate of speciation is a matter of the length of generations rather than time. Humans generally generate somewhere between sort of every 15 and 20 years, right? There's a new generation, roughly. It takes us that long to mature. And even then, you can't really reproduce more than about every, 18 months to 2 years. It can happen, but it's actually much less likely to. So even at the fastest rates, though, we don't come close to, say, mice, who may have several generations within a year, 5 or 6. That's really different. What that means is the genes are being passed on faster in terms of normal time, But if you're just counting generations, it may take, a number of more generations. So, in Darwin's time, they thought speciation was a slow process of accumulating mutation after mutation, that mutations were very rare, and it took a long time to collect enough mutations to have a real effect. But that didn't answer some big questions. A number of biologists, starting in the 1970s, pointed out, hey, if this is the case, why is it when we look at the fossil record, we often find these periods where it's almost like changes occurred overnight? Like, suddenly, there's a change that's there with almost no intermediate fossils. How does that happen if it's slow and gradual? If it's slow and gradual, we should see a steady pace of change, but we don't always see that. And we're talking about macroevolution here. So microevolution is changes in gene frequencies within a species, and macroevolution is actually the formation of new species. So punctuated equilibrium was a school of thought that started in the 1970s with Niles Eldredge and Stephen Jay Gould. And it says that instead of being a slow process, gradual sort of accumulation of mutations, there are long periods of steady states and stability in evolution, punctuated by periods of very rapid change. So it looks, instead of looking like this, like slowly going up, it looks more like you're hopping up every so often. And the idea would be that basically environments are relatively stable for a time and then suddenly will sort of go unstable, but they'll reach an equilibrium again very quickly, but in a different way. And during those times, natural selection is working overtime. And it's during those times that you see these rapid changes with not much intermediate in between. Now, since their time, and here illustrates sort of the difference here. On the left is the phyletic gradualism. That is, new taxa are produced through slow accumulation of changes over time. Whereas on the right is punctuated equilibrium. We're going along and boop, now we've got an orange butterfly. Going along, boop, now we've got a purple butterfly. Who's right? The truth is probably both. Since Gould's and Eldredge's time, I think a lot of the opinion has swung back to the idea that, well, by and large, it's a gradual process, but there's also a lot of this punctuated equilibrium happening too. You can't deny that it's happening at all. So maybe it's a picture of both that is going on, that the process of evolution is a flexible one in that respect. So in that case, we should expect new species to arise when there are big disruptions. Certainly right now, there are huge selective forces going on in our world because of climate change. They have already begun. They were already begun because the spread of Europeans around the world has put massive stress on ecosystems everywhere. This had already started resulting in a massive die-off, massive loss of biodiversity, beginning even 200 years ago, fully accelerating in the late 20th century, and with the onset of climate change and hotter temperatures. Hotter temperatures overall doesn't mean everybody's getting hotter. It means weather is more extreme. And those extremes are what are going to start acting as natural selection. And we're going to start seeing some species adapting and some failing to adapt. And that is the long story. We are a force of evolution. That shouldn't surprise us because other organisms do this too. alter their environment through their very existence, sometimes in such a way that they alter it so much that they kill themselves. So, they drive themselves extinct. So we might want to think about that. That is all for today. Sorry to leave you on such a dreary note. But I hope you are doing well. Take care of yourself, and I will see you soon.